Okay. Well, my name is Floris Gieshoff. I work together with Zeno Geraat for the Netherlands Forensic Institute on digital camera identification. So my presentation will be about linking camera to images using PRNU noise. The process of digital camera identification focuses on linking images to the source camera or linking images to other images in a database to determine if they have a common source. So what are the uses for digital camera identification? Well, let's say you find child pornography images on someone's computer and you wonder if this person actually made these images. What you can do is you can then take his camera and try to link these child pornography images to his camera. You can also do this with movie piracy and pretty much any case where images and digital camera is involved. Let's say you don't find a digital camera, you could also see if you can find, say, vacation photos or images on Facebook or other social networks. How does this work? Well, each camera, when you take an image, leaves random noise and systematic noise in the image. A part of the systematic noise is photo response non-uniformity. You can extract this noise, we call it PRNU pattern, and it serves basically as a fingerprint for the camera. Every image taken by this camera will have the same fingerprint. This PRNU noise is caused by imperfections which happen during the manufacturing process of the camera sensor. Basically, it results in that the pixels give a slightly higher or lower value than it actually should. So far, research has indicated that it's unique for every digital camera. It's also in webcams, phones, videos, etc. So you have the camera, you have the image, and then you can extract the PRNU fingerprint, which you can see in the bottom right, an example. So basically it involves 3 steps. The first step is to extract the PRNU noise, to extract the fingerprint with a denoising filter. The most popular one is the wavelet denoising filter. At the NFI we have developed our own filter, which is about 10 times faster and just as accurate. The second step, the problem with the filters is that they're not perfect. They don't extract only the PRNU noise, they also extract the random noise and some scene content as well. To make a better quality fingerprint, you could use multiple images of the same camera, say 20 to 50 images, and make an average estimation of the fingerprint. Of course, you can only do that when you have a suspect camera. So, in case of a database where you want to know if there is a common source between the images, you can skip the second step. The third step is to compare the fingerprints to each other. You have several options for this, like the Pearson's correlation, the normalized cross correlation, and the peak to correlation energy ratio. They're all related to each other. At the NFI we use the second and the third, so the NCC and the PCE. So now I will talk about a case example. Some burglars were making images during breaking into a house. Later the police had a suspect and they found these images on his computer. While the perpetrators, while breaking in, were wearing masks, so they could not be recognized. The police also found a BlackBerry phone with a camera, and then they came to us. And asked us if we could tell if these images were made with the seized camera. There was, however, a problem. The BlackBerry phone didn't work anymore, so we couldn't make images. There was, of course, also a possible solution, and that was to take out the image sensor from the broken BlackBerry and place it into a new BlackBerry. So before we do it with the seized BlackBerry, we had to do some experiments. So we got several BlackBerries, 11 in total, and before we switched, we first tested how well it worked to do camera identification. What you see in this graph is the device numbers, 11 in total, and when you compare images from device 1 with other images of this device, you get approximately 1.4, a score of 1.4, and all the others, as you can see, are all around 1.2 if they come from the same camera. If you compare the peer new pattern of the different BlackBerry devices to each other, you see you get a score of around 0.1. So there's a big difference between matching values and mismatching values. Then we started the switching. It was relatively easy. It takes about 5 minutes. In the top left you see the camera module. It's just a little square. On the right you see a close-up of what it looks like when you take it out. So when you put it back in, close the BlackBerry, it will work again. The question was if the switching of this module will have any effect on the peer new pattern. So these are the results after switching. So what you see is on the x-axis you see ID 4, so BlackBerry number 4, with its own sensor, with the image sensor from BlackBerry 4, compared to the BlackBerry number 6, which after switching had the sensor from BlackBerry number 4. And when you compare them, you see they still match. So the BlackBerry itself does not seem to affect the peer new pattern of the image sensor. This means we could do the same with the suspect's BlackBerry, which is what we did. So the results were that it was very much more likely that the seized BlackBerry was indeed the source of the images and not another camera. We also published a paper about it. In the paper is also a YouTube link which shows the switching of the image sensor. Next, I will talk about a current project we are working at the NFI. A few years ago, we started with the development of a software solution for camera identification called PRNU Compare. However, we noticed that when you have a large case, it's basically too slow to help. So the previous case with the BlackBerry, it was fine. The software was fine. It went fast enough. But when you have a large database for example, a child pornography case, they can have thousands and even millions of images. And if you want to compare these, it's going to take years to compare all these images. So we started working on PRNU analysis data. In short, it's PANDA, which is meant for fast camera identification for large cases. And it's supposed to be suitable for a modern desktop computer. Because maybe you heard yesterday in Brazil they have this computer cluster for research, but of course not everyone has such a nice system. So we wanted to work on a decent desktop computer. So the normal process in our old software, when you extract a peer new pattern from a 5 megapixel image, it takes up about 60 megabytes of space. This means that reading and writing of a peer new pattern can take up quite a lot of time. It also means that you can only store a limited number of patterns in the memory, which slows down the comparison of these patterns. So when you use this software, when you use our old software on a 2.3 gigahertz quad-core computer, and you have a database of 100 images, which you want to compare to each other to find a common source, it will take you about 3 hours. So in Panda, we used the filter that we had developed, which was about 10 times faster than the old one. We also convert each image before extraction to grayscale, because we found out that using color does not increase the accuracy over grayscale, which means the pattern is already reduced to 1/3 of the size, because you don't have the red, the green, and the blue channel, but just one single intensity channel. Then we do a digest on the peer new pattern. This means that we select only the highest absolute values of the peer new pattern, and you can say you can take like 5 or 10% of the total pixels. This results in a one-dimensional array, a one-dimensional matrix with all these peer new values. The advantages of this are that the pattern is only around 2 megabytes instead of 60, which means faster reading and writing. 1D cross correlation is a lot faster than two-dimensional cross correlations, and you can keep a lot more patterns in the memory. Of course, the disadvantage is that you throw away a lot of information. The question is, how does this affect the accuracy? So, some preliminary results, because we are still in the middle of development of this. We can now do 500 comparisons per second on the same computer I mentioned before. This means that the small image database of 100 images would now only take around 10 seconds instead of 3 hours. The output will be, well, as you see here, the first output will be something like this matrix you see here with all the cross-correlation values. Of course, it's a bit hard to interpret this. So we developed a new method. We call it clustering. From this large matrix with all the numbers, when they are above a certain threshold, we assume these images come from the same source. These images are then clustered together, which means that we take the peer new pattern of these images and merge them together for a better peer new pattern. However, instead of taking the real peer new pattern, all we need is the cross correlation scores from the previous matrix. The final result is a cluster of images that basically come from the same source. So before clustering, I made a heat map of the matrix. The black pixels, each pixel is a cross correlation score, and the black pixel or the dark colored pixel means it's a low cross correlation score, and when it's white, it means it's above the threshold. On the right, you see the results after clustering. Every white square means it's a camera. So all pixels in the white square belong to the same camera. So another way to visualize this is as follows. Every color is a cluster. Every color is a different camera. So what we do is we take every picture that is above a certain threshold, and then we compare it to all the images in the same cluster except that certain image, and then we check what the correlation value is. So when it belongs to the cluster, you will see a somewhat higher results, like somewhere around 0.005, and on the bottom you can see when it doesn't belong to the cluster, it will be somewhere around 0. So in this cluster we had 9 cameras. In total we had 1283 images, which means about 820,000 comparisons. The true positive rate we found was 100%, so we found that every image that belonged to a certain camera was indeed found to be of that camera. We also had 0 false positives. Then we tried a larger set with different cameras. In total we had 30 cameras, which means 4.5 million comparisons. Here it says the true positive rate is 75%, but since yesterday we managed to get it up to 96% true positive rate and a 0% false positive rate. But there is still some room for and possibilities for improvement, and well, the functionality should be increased, and we're going to work on that in the next years. Thank you for your attention, and if there are any questions, feel free to ask.
We're checking the. Thank you very much, Floris. We're checking the online system to see if there's questions for you. Bear with us 1 second. While we're loading here, there's another question. Floris, if you're still on.
Yeah, I am.
Yeah. Yeah, I am. There's a question for you.
Hello.
Hi, Floris. It's Alencar from Haskell.
Hey, I'm fine. How are you doing?
Fine, thanks. Floris, it was a very interesting the results from NFI, and as you know, you are working on the methodology, and you have including running some trials there. But one question that I'd like to ask to you is about, for example, what kind of image you are using to create the profile for device. For example, in the literature, we found during our research that many researchers using controlled image, like image from blue sky or some kind of color grids. And today you are using natural colors, pictures, and how you are running the trials considering the group of images for fingerprints to create the profile.
Well, when you have the access to the suspect's device, it's indeed best to take pictures from like a gray wall or the blue sky, because it's the easiest way to extract the pattern from that.